So today we're going to continue our discussion on enzyme kinetics, or enzymes in general, and specifically talk about the kinetics of enzymes, or specifically what kinetics are the rate of reaction that enzymes catalyze reactions. And remember, when we're talking about an enzyme catalyzed reaction, we're talking about the enzyme plus the substrate, making some sort of enzyme substrate intermediate to convert the substrate to product, and the enzyme is still present. And we'll see this reaction over and over again in chapter 6, part 2. So there's several different ways to study mechanism as biochemist. But first, what I want to say is that we will not be specifically covering chapter 6, part 3. But this particular section is investigating mechanism. And so if you're having a hard time understanding the different mechanisms, so acid-base, remember these are 3 different types of mechanisms: acid-base, covalent catalysis, and metal-assisted. I really encourage you to use your textbook as a resource in order to investigate mechanism further in chapter 3, section 3. All right, but we will not be going into detail in this section at this time. Okay, so in order to understand mechanism, we need to study it biochemically, and we can do this in a couple of different ways. First is to determine the 3-dimensional structure, as we talked about in our last section in chapter 5, either by X-ray or NMR. These 3-dimensional structures can tell us a lot about X-ray and catalysis. We can also do site-directed mutagenesis, where we change amino acids and determine or study the effect that change has on the rate. Or mechanism in general. We can study the rate of a reaction, or enzyme kinetics. This is often termed Michaelis-Menten kinetics as well. And this is the focus of this chapter 6, part 2. Okay? And so how the rates of reaction change in response to experimental parameters. All right, so rate is affected by the presence of an enzyme, by lowering the activation energy. We've already talked about that. By the presence of different substrates, we'll talk about. By the presence of effectors or modulators. Remember, these can be positive modulators or negative, which means they can enhance or actually inhibit the rate. And we'll talk about this again in at the end, we'll talk about inhibition of enzyme kinetics, as well as temperature. Remember that according to our Gibbs free energy, no, we don't want to talk about that, but they can be affected by temperature. All right. So we know when we refer to rate of reaction, we know that rate is equal to the velocity or the activity. We've seen this term before. When we talked about enzyme protein purifications, we talked about activity assays when we talked about what an assay was, and compared the difference in activity assay measurements, measuring the rate of a reaction, to measuring the total concentration of reaction by either ELISA, Bradford, or the absorbance at 280, or the kinetics. These are all the same type of term. And so the units are either referred to as either units or concentration of your substrate or product per unit of time. We'll talk about this again in a little bit. Or the number of moles per time. So it's always some sort of concentration per unit of time. And we can write a rate law to express the conversion of our substrate and relate it to our rate constant K. All right, and so let's talk a little bit more about this. This is just review from introductory chemistry. So the the reaction rate or the velocity is equal to the appearance of product over time. All right, and that's essentially what this is saying. So D is just the derivative or the change in product over the derivative of time or change in time. So this would be the appearance of product over time. So you would get a positive rate, right? This would be the disappearance of the substrate. So A is the substrate. As the reaction is occurring, the substrate is being removed from the reaction. So it would still be change in substrate over change in time. And that's negative here, again, because we're losing substrate as the reaction converts substrate to product. This can be also expressed as a rate law, where A is obviously the concentration of substrate, and K is termed the rate constant. Okay? All right, the rate constant is a proportionality constant. That just relates the overall rate to the concentration, and its units depend on the rate order. Okay? So the rate constant can be affected by the concentration of reactants, temperature, the presence of an enzyme or catalyst. An enzyme is a catalyst, or the pH. And so your reaction order relates the reaction rate with the concentration of reactants or substrates through the rate law expression. I will put a review material just covering basic rate laws and information on rate constants on the As You Learn site so that you can look over that. Okay, so here we have our rate laws, and so a zero order reaction here has a rate expression or a rate law equal to rate equals K. It is not affected by the concentration of substrate or the presence of substrate. Okay. The rate of the first order rate law is affected, is proportional to the substrate concentration. Okay. So here, for zero order, the units of K would be equal to rate, so usually some sort of concentration over time. Whereas here we have a unit of concentration. So for first order, we have a unit of concentration, let's just say molar. The rate would be molar per second. So K would have units of inverse time, or 1 over time. Okay, and that's kind of how you can determine whether your reaction order is 0, first, or second, depending on the rate expression and the value of K. All right, I do want you to say that, or I do want to mention, this is very important, I'll put it in red, that you cannot determine the reaction order by the balanced chemical equation. This is very important. You must have experimental data. This is extremely, extremely important. All right, you must have experimental data. All right, so let's do a clicker, or I guess just a problem in class, showing just how you might see these types of questions on an exam quiz or in your homework. All right, so the following reaction rate is first order, so I tell you it's first order with respect to each reactant or substrate. And so we have two substrates, nitrogen dioxide and ozone, all right? And I tell you it's first order. Again, we cannot look at the amount of reactants and the balanced equation to tell us whether it's first order or not. But I ask you to write the rate expression for this chemical reaction, all right? And I guess, I do say, okay, with respect to each reactant. And so rate expression is always the rate is equal to the rate constant, K, times the concentration of nitrogen dioxide times the concentration of ozone, okay? And so there's a 1 implied here because the following reaction is first order with respect to each reactant or substrate. So if we double the nitrogen dioxide, the rate will double. Oh, that's the second part. If we double the ozone, then the rate will double. So it's first order with respect to each substrate, but that makes it second order overall, the rate. Okay? Okay, so I accidentally hit the monitor screen and it closed off the video. So let's try this again. All right, so the rate of the reaction is second order overall. And so if we double the concentration of one of the substrates, nitrogen dioxide, how would the overall reaction rate be affected? And so I just said that the reaction rate would also double. If we triple the concentration of ozone overall, how would that affect the reaction rate? Because it is also first order with respect to the overall rate, it would triple. Okay, and so those are some of the questions that you may see. And again, there'll be some on your homework as well. Okay, so that's just some general information on kinetics, again, from hopefully a review from intro. And again, there's a document on the As You Learn site that will tell you a little bit more about rates, rate constants, overall, first, second, and zero order rates of reaction. So how is this measured in an enzyme or enzyme kinetic measurements? So the experiment that you would do is measuring the rate of a reaction under variable parameters. All right, so in this example, you're measuring the rate, so you're measuring over time, remember, the amount of product that is produced. And so remember, we're measuring the change in concentration of product over the change in time. And so as you're measuring the rate of the reaction, you're changing your amount of substrate concentrations and measuring the rate of reaction. Okay, and this is figure 6-10 from your textbook. So this, the key factor for this experiment is the concentration of your substrate. So the concentration of substrate changes, again, as substrate is converted to product. We are going to, when we're measuring enzyme kinetics, examine the initial velocity or V naught. This is key, all right? So you can see that the initial velocity is linear. That's what these extrapolated lines are showing, initial velocity. And here. And that over time, the amount of substrate, all the substrate that you've added has been converted to products, so you get a plateau and no more product is made. So we don't care about that part in the reaction, okay? So no more product is made, the data levels out. So I mentioned this term Michaelis-Menten, and that's essentially what measuring the initial velocity is in the presence of different substrate concentrations. I always spell this wrong, so let me take a minute. So this is Michaelis-Menten kinetics, and this is just the most simple example of enzyme kinetics. So not all enzymes follow Michaelis-Menten kinetics, but this is the simplest example for us to talk about in this course. But I want you to know that not all enzymes exhibit Michaelis-Menten kinetics. Okay. So we've seen this reaction before where we have the concentration of our enzyme plus the concentration of our substrate yields this intermediate, this enzyme substrate intermediate complex, and generates our product and our enzyme. All right, so there's two steps. There's step one, or phase one. Step one. This conversion from enzyme to substrate, to generate this enzyme substrate complex is extremely fast. It's reversible, which means it can go in the forward or reverse direction. That's why you have two rate constants. You have a K1 and a K minus 1, and this is termed pre-steady state. Okay, so it's very fast, very reversible. It's termed pre-steady state. And this describes the formation and breakdown of ES. Obviously, formation in the forward direction, K1, and breakdown in the reverse direction, K minus 1. All right, and so the second step and I'll do this in red, is the ES conversion or breakdown to product. It's a slower step, which makes it the rate determining step. We term this step the steady state because it is the rate determining step. It's dictating what the overall rate of the reaction will be. All right, so we can write rate equations for each of these three rates. The K1, so the forward direction, the formation of ES, so ES formation. Oops. And I'll put this in black just so you can correlate it above. And remember, this is fast, pre-steady. This is equal to K1 times the concentration of E times the concentration of S. And so we know that it's second order overall. The breakdown of ES, again, breakdown is still fast in terms of K minus 1. And this is actually first order. And then the conversion of ES to product is also first order. And because this is the rate determining step or the slow step, so this is also breakdown, but it's red, I'm sorry, red. Because this breakdown is so slow, it's the rate determining step, and really the reaction that we're going to look at when we measure enzyme kinetics. Or we'll say that this dictates the overall rate of the reaction under steady state conditions. Michaelis-Menten kinetics. All right, one of the assumptions is that the concentration of this enzyme substrate complex remains constant over time. So what does that mean? It means that the change in the concentration of ES is essentially 0. All right, and this is a very, very important assumption to make because it allows us to look at the sole formation of product given current conditions. All right, so it remains steady state over time. You may notice that there's no K minus 2. All right, so there's no K minus 2, again, because we're looking at V naught, or the initial velocity. And because we're looking at initial velocity, you can assume that no products are generated. if no products are generated, that we can't convert products back to ES. All right, so that's why there's no K minus 2. Okay. So let's look a little bit more at this Michaelis-Menten plot. All right, so this is the data that you'll generate when you run a Michaelis-Menten plot. So remember, the rate of the formation of ES is equal to the rate of consumption, which means the overall change in the concentration of ES over time, which is what I just said, is 0. That's very, very important. And this is because the first step, the conversion of E plus S, or the reaction of E plus S to yield ES, is extremely fast. And it makes lots and lots of this intermediate. Okay, that's a very important assumption. The other important assumption is that we're measuring the initial velocity, that linear rate before saturation occurs. That's the other important assumption that we make. So anytime you are plotting a Michaelis-Menten kinetics data, you have to plot, again, our substrate concentration is on our x-axis. Remember, concentration of substrate or ligand, remember ligand is just a specific substrate for an enzyme, is plotted on the x-axis. Now the y, instead of being a theta, like we saw in hemoglobin, is actually the initial rate, or V naught. All right, so that's your y-axis. And you're able to get some sort of hyperbolic curve that looks like this. Well, what is this data representing? What it's representing is that initially, this is a little cartoon that kind of correlates the data to a cartoon, which I kind of like. What you have is over here at low substrate concentrations, you have more enzyme substrates or more enzyme active sites than you do substrates in order to generate a lower velocity. And so you're not saturated yet. Every time you add a substrate, it's going to be converted to product. And so you have a first order reaction. Okay? You keep adding you keep adding substrate until at some point you've saturated all your active sites. And so no matter how much substrate you add, no more product can be made. And so here we've termed 0 order, because the rate will not be affected no matter how much substrate you add. All right, so the Michaelis-Menten plot is kind of a combination between first and second order. Oh, not first and second, I'm sorry. First and 0 order. This is extremely important. There is no second order. The Michaelis-Menten plot is a combination between first and 0 order rates, where over the linear portion, you have first order. When you add substrate, you get higher velocity, and where it's kind of plateaued out, you have 0 order. No matter how much substrate I add, if I keep adding, no more, the velocity won't increase anymore. Okay? And so this term where the plateau reaches has a specific term known as Vmax, the maximum velocity of the reaction. And that's just kind of defined down here. Okay. So the equation that represents Vmax in relationship to your substrate concentration and your velocity is termed the Michaelis-Menten equation. And that's represented by this blue box. So remember, if it has a blue box around it, that means you're required to know it. And so this should look very similar to the theta equation that we used for myoglobin binding oxygen, or its ligand, where instead of theta, now we have a rate, and that's equal to the maximum velocity times the ligand concentration over Km. We'll talk about Km in just a second. plus the substrate concentration. All right, so you can determine all of these parameters experimentally. And those of you in lab will do just that. And you'll determine the Km and Vmax of your substrate for your protein. All right, so what is a Km? A Km is referred to sometimes as a Michaelis-Menten constant, and essentially all it is a rate law expression or a rate constant expression. So really what Km is doing is it's relating the ES formation, so for the formation of that important intermediate to the consumption or breakdown. Okay, and the expression is shown here, where you're again comparing the rates of breakdown or consumption of ES to the rate of formation. And we'll see how much this Km is changed in the presence of inhibitors. Sorry. Just like with our KD value, so Km is very similar to KD. I'm sorry. The substrate at which the half the enzyme's active sites are occupied by substrate is also a definition of Km, and so it's very similar to KD. All right. So let's kind of go a little bit more detail into what that means. So remember from the previous slide that Km, just like KD, this is just like KD. All right, and we'll compare the two in just a second. But just like KD, Km is a substrate when the maximum velocity is equal to 0.5. So you have a maximum velocity shown here. You can estimate what the half velocity would be, and just like KD, Km is the concentration of substrate, so it should always have units of concentration, always, at half Vmax. All right, so we have our expression for the Michaelis-Menten equation. We can relate that to theta. Instead of just binding, now we're looking at a rate. All right, we know that if substrate is equal to Km, we can plug it in for the above reaction. So substrate is equal to Km. So now we have that the initial velocity is equal to the Vmax, or Vmax over 2. Oops. Or 1/2 Vmax, or 0.5 Vmax. All of these are the same way to write that the when the Km is equal to the substrate concentration, that's how you get 1/2 Vmax. All right. So let's look a little bit more into this reaction, all right? Or the comparing Vmax, this equation, this Michaelis-Menten equation. So let's get into comparing the relationship between Km and KD. So they are very, very similar. They essentially use the exact same equations like I just showed you here and here, except now we're measuring a velocity, so an actual rate, whereas before we were just measuring binding. So yes, it's there, or no, it's not. Now we're measuring velocity or conversion to product. So we're just measuring chemistry. But fundamentally, they are the same thing. All right, so here's our myoglobin plot, measuring theta, where we have theta is equal to the concentration of ligand over the KD plus the concentration of ligand. Now we have the initial velocity is equal to Vmax, so the maximum velocity, times your substrate. Remember, your substrate is just a ligand for your enzyme. over the Km, which is the Michaelis-Menten constant that measures the formation of breakdown and compares it to the formation of ES and compares it to the breakdown of ES plus your substrate concentration. One thing I want to mention that's of importance is this Vmax. See how it's extrapolated over the line? This is very common in Michaelis-Menten data, is that you have to estimate your Vmax value. So we'll talk about what a better way to measure Vmax is than plotting your hyperbolic curve. So you don't get, so Vmax is a constant, but it's hard to determine with this data. So hard to determine exact value. With a Michaelis-Menten plot. And we'll talk about a better way to plot your data on Friday. Okay, so just like our KD, our Km is low when we have tight binding. So the better the substrate, or the tighter the substrate, the lower the Km, just like KD, okay? All right, so I think we'll do one example and then we'll stop here and pick up on Friday. So this is an example from your textbook. The enzyme happyase has recently been discovered. Below is the reaction it catalyzes. It's catalyzing sad to happy, so snow day versus the time you get to spend with me. It gives you an enzyme total concentration of 20 nanomolar, your substrate concentration, which is SAD, right, is 40 micromolar, and the initial velocity is 9.6 micromole per second. It's asking you to calculate the Km of the substrate SAD, and it provides you with the Vmax. So the equation that you use would be the Michaelis-Menten equation. V naught is equal to Vmax times your substrate concentration over your Km plus your substrate concentration. And again, we're trying to calculate the Km in this equation. So let's assign our variables. 9.6 micromole per second. Nope. Yes, that's right. Is equal to 12 micromole per second. Make sure those are on the same units. So for this example, everything is in micromole, so that makes life easy, but just make sure everything is always in the same units so that they can cancel out. Plus 40 micromole. Okay? You multiply your denominator by 9.6, and so you're left with 9.6 micromole per second times Km plus 40 times 9.6, I get 384 micromole squared per second is equal to, you multiply these two together, 480 micromole squared per second. Subtract both sides by 384 micromolar per second. To get rid of this, and so you're left with 9.6 micromole per second is equal to, I get 96 micromole squared per second. Now you divide each by 9.6 micromole per second. Your per seconds will cancel out, and one of your micromole will cancel out, and you're left with 10 micromolar for your Km. Remember, Km is the concentration of substrate at half the Vmax. So the biggest mistake students make is that when they see that a Vmax is equal to 12, they tell me that the Km is equal to 6 micromole per second. That is not the case, right? And so if we have concentration of substrate here over initial velocity, and we have a Vmax of around 12, half the Vmax would indeed be 6, but the Km is the concentration of substrate. So you would need the experimental value to tell you that this concentration of substrate is actually 10 micromolar. Okay? All right, we'll stop there and we'll talk about a better way to estimate our Vmax other than a Michaelis-Menten plot shown here on Friday. Okay, have a good day. Bye.